Well, hi there, boys and girls. Today we're going to look at some particle motion, and we're going to be looking at how position, velocity, and acceleration are related to each other, and what that tells us if we have this little particle moving along a line. So I've got a particle moving along a horizontal line, so that means it's going either to the right or it's going back to the left, one of the two. It's going one of these two directions, but it's staying on that horizontal line. And its position is given by this function, s of t equals, and s is measured in meters and t is measured in seconds. So we're going to find the velocity at time t and at t equals 1 second. So this means I have to find an expression for v of t. Now v of t, your velocity, is going to be your first derivative of your position. So it's s prime of t. So that's going to equal 6t squared minus 14t plus 4. So that is my velocity at time t. And then we have to find the velocity at 1 second. The velocity at 1 second, well, I've got v of t. I should have written v of 1. Let's try that again. Let's write v of 1. I'm going to plug 1 in for t, and that will give me 6 minus 14 plus 4, and that works out to be negative 4, and this is meters per second. Alright, when is the particle at rest, moving left, or moving right? Well, at rest, we need the velocity to equal 0. Now, to be moving left, we need our velocity to be negative. And to be moving right, we need our velocity to be positive. Justify your answers. And that's what I have here as my justification. So I just have to do the math to figure it out. So let's first of all figure out when the velocity is 0. That's the easiest thing to do. When is the particle at rest? Now my velocity was my expression up here, 6t squared minus 14t plus 4. And to set that equal to 0, I'm going to need to factor it. So I'm going to say that my velocity is, let's factor out a 2. That will give me 3t squared minus 7t plus 2. And I should be able to factor this. It's not going to be too bad into two binomials. This has to be a 3t here. This will be a t here. I'm going to have a minus 2 and a minus 1. Let's see if that works out. 3t squared minus 6t minus 1t. There's my middle term, minus 7t, and then plus 2. So this is my velocity factored out. And so if we set this equal to 0, there's going to be two places where it equals 0. 1/3 and 2. That's two places where it equals 0. So I'm going to say that we are at rest whenever t equals 1/3 and t equals 2. So the particle is at rest for these two values for t because v of t equals 0. Now let's figure out moving left and moving right. And that's where a number line is going to help us very, very much here. So I'm going to go grab a line. Get back here. Grab a little line. We're going to do a little number line test for our velocity, and this will tell me when it's moving left and when it's moving right. I need my velocity to be negative to be moving left, and I need my velocity to be positive to be moving right. Get back to my purple pen here, and I'm going to have 1/3 and 2 on this number line, and these are the critical points. So I'll check values for my velocity, and this will tell me what my position is doing, what's happening to my position. So we're greater than or equal to 0, so let's plug in a number like smaller than 1/3, like 1/4. If I plug in 1/4 into my factored expression, I'm going to get 3/4 minus 1, which is going to be a negative, and then 1/4 minus 2 is also a negative. I'm going to have a negative times a negative. My velocity will be positive here, which means my position, I am moving to the right. Now let's plug in a number bigger than 1/3, like say 1. If I plug in 1 into my factored form for my velocity, I'm going to get a positive times a negative times that 2, which is going to give me a negative, and that means that my position, I'm moving left. And then to the right of 2, like 3, if you plug that in for your factored form of your velocity, you're going to get a positive velocity, which means that you are moving to the right. So I don't have a lot of room here left, but I'm going to say that the particle is moving left. Let's do that one first. On the interval from 1/3 to 2, because v of t is negative. And then I would say, quote, 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 particle is moving right on two different intervals. I'm moving to the right from 0 to 1/3, unioned with 2 to whenever I feel like stopping. It didn't tell me, it just says greater than or equal to 0. And I would say because v of t is positive on those intervals. Okay, so let's answer the next one. Find the acceleration at time t and t equals 1. Now your acceleration expression is going to be the derivative of your velocity, which happens to be the second derivative of your position. So my acceleration expression is going to equal, where's my unfactored form for velocity? Up here. So there's my velocity. I need to take the derivative of 6t squared minus 14t plus 4. So that's going to equal 12t minus 14. So that is my acceleration at any time t. Now we want to find it when t equals 1. So a of 1 is going to equal, plug 1 in for t, and you're going to get 12 minus 14, which is negative 2. And this will be meters per second per second. Alright, so let's answer the next part. Find the displacement of the particle between t equals 0 and t equals 3. Now this just means where you ended up. When you leave your house in the morning and when you come back home, your displacement is 0 because you are right back where you started. So what this is asking is how far from the beginning did we end up? So I simply need to do s of 3 minus s of 0. I need to just subtract these two. And I have on a calculator here, you can't see it, but s of 3 was equal to 8 and s of 0 was equal to 5. And this, my displacement is 3. The meaning of this answer is the displacement was 3 units to the, well actually, and our units was meters. Our displacement was 3 meters, and since it's positive, we were to the right. 3 meters to the right. So after these 3 seconds, we went back and forth and back and forth. We ended up 3 meters to the right of our starting point. That'll see a little easier to see. Alrighty, so now let's scroll down here for the distance traveled. Now this is a little different. You can't just look at the displacement. For example, what I talked about earlier, if you leave your house and you come back home at night, your displacement might be 0, but you actually traveled a lot further than 0. So we have to look at when our particle changed its direction. When did it turn around? Now we already know there's only 2 places where our velocity was 0. Our velocity was 0 at 1/3 and at 2. We moved to the right, then we turned around and moved back left, and we turned around and moved back right. So let me show you how I would organize this. I will have this little table, t and s of t. And I'm going to get these from a calculator, and I'm going to plug in all of our critical points and our endpoint. So 0, 1/3, 2, and 3. 1/3 and 2 were critical points. They came from where the velocity was 0. That's where the particle can change direction. And then 0 and 3 are my endpoints. And I plugged these in on the calculator, and I got 5. At 1/3, it's 5.6296. At 2, it was at 1, and 3, it was at 8. So let's talk about what happened here. Now, you can see here we ended up 3 meters to the right of where we started, but we went a lot further. We went 5 units to the right. So let's find our distance traveled. Our distance traveled is going to be 5 units to the right. Then we turned around and we came, well, actually, 0 to 1/3, that's where we started. I'm sorry. We started at 5. So we moved from 0 to 1/3. We moved 0.6296 away from our beginning. So I'm going to subtract these two to get 0.6296. From 0 to 1/3, we moved to the right, and we moved to the right this amount. Then we turned around and went back left. Between t equals 1/3 and t equals 2, we moved to the left, and that is from this sign chart right here. We were moving to the left, and we moved all the way back on the number line to 1. So if you subtract these two, you get 4.6296 by subtracting these two. So we moved to the left that amount, and then we moved around. We turned around and went back to the right from 1 back to 8, and that is a distance of 7. So you just have to go through and subtract these values and add. We're basically adding up the absolute value of our velocity to get our distance traveled. And so anyway, that's going to be my answer, 0.6296 plus 4.6296 plus 7. And so let me see what that is on the calculator here. 0.6296 plus 4.6296 plus 7. Looks like we traveled a total distance of 12.2592 meters. Whenever we learn integration, we're going to find another way of doing this, but for now, that's what we're stuck with. Okay, so now we're going to talk about speed. Speed is the absolute value of velocity. Speed is the absolute value of velocity, and it's always going to be positive. And we want to know when a particle is speeding up, slowing down, and this hint tells you exactly how to do this. You're going to be speeding up when your velocity and acceleration have the same sign, and you're going to be slowing down when the velocity and acceleration have opposite signs. So let me show you how I would organize this information. I would draw a line, and I would put all of the critical points not only for velocity but also for acceleration. So we found out that we started at 0, we had a critical point at 1/3, and we also had a critical point at, see if I can go back here. Whenever our acceleration, well, I actually didn't find that, did I? I'm going to set my acceleration equal to 0 to find another critical point. So I'm going to say acceleration changes sign at t equals, that's going to be what, 7/4? No, I don't think it's 7/4. It's going to be 12t minus 14 equals 0. Let's just write it out. So 12t equals 14. So t equals 14 over 12. I think it's 7/6. Yeah, 7/6. I shouldn't have tried to do that in my head. So I'm going to put 1/3, 7/6, and 2 on my number line, because that's when my velocity would change sign. And we're going to see if we can organize this. We're going to have our velocity, and we're also going to have our acceleration. I'm going to write down here what my acceleration equation was so I can make sure I have that correct. My acceleration equation was 12t minus 14. Okay. And let's go ahead and just do a number line for this real quick. There's only one critical point for this, and that happens at 7/6. And let's check our acceleration. Our acceleration at 1 would be negative, and our acceleration at, say, 2 would be positive. So I know my acceleration on those intervals. So let's see what happens here. From 0 to 1/3, our velocity was positive, and our acceleration from 0 to 1/3, 1/3 is less than 7/6, so our acceleration would be negative there. Now from 1/3 to 7/6, we go back to our table. 1/3 all the way out to 2, my velocity was negative. We don't want to get to day 2 yet. My velocity was negative here, and my acceleration on this interval from 1/3 to 7/6 is also still negative because I haven't reached 7/6 yet. Now from 7/6 to 2, my velocity is still negative, but my acceleration has turned positive, and then after 2, they're both positive. So my answer to this question is we are going to be speeding up whenever we have the same sign for velocity and acceleration. That's speeding up. And then when we have opposite signs, that's when we're going to be slowing down. So we're going to be speeding up on the interval from 1/3 to 7/6, also from 2 to infinity, because velocity and acceleration have the same sign. They're either both positive or both negative. Have the same sign. Alright, and then we're going to be slowing down on what intervals? We're slowing down. Let's see, it looks like from 0 to 1/3, they have different signs there. Also, from 7/6 out to 2, we're slowing down because velocity and acceleration have different signs. I'll just do diff signs. All right, so that's enough for that, and I will see you guys tomorrow.